Okay. Good morning. Can I start now?
Yes, sir.
Good morning,
Morning.
sir.
Okay. Okay. Let me just give the information related to last class what we have discussed. That is, in the second case 2, what we have considered that k delta is finite, means the control actuator stiffness is finite. With that we could get two different equations, equilibrium equations, and solving those two equilibrium equations we calculated theta and value of delta. After substituting the value of theta and delta, we have calculated here the aeroelastic lift due to both flexibility of the wing and also the control surface. And we have taken this LR, that is rigid lift, that is Q into C into CL delta into delta naught. And then we have calculated the efficiency. Eta delta is equal to LAE divided by, means aeroelastic lift divided by rigid lift. And then finally we got this expression 1 minus Q bar into 1 minus B into B divided by CL delta bar, then whole thing divided by 1 minus Q1 bar multiplied by 1 minus Q2 bar minus BC Q1 bar Q2 bar. So if you look at here, this expression, when it becomes zero, that is numerator part of the expression eta delta is equal to zero, that will give us the condition for control reversal. That's what we got it here. With the control reversal, eta L equal to zero, then we are taking the numerator equal to 0, that is 1 minus q1 bar multiplied by 1 minus b by CL delta bar equal to 0. And then after manipulation and final substitution of the values, whatever non-dimensional parameter we considered, it is coming as QR is equal to minus QD wing, whole thing multiplied by CL delta bar by
Sir, your voice is not audible.
Sir, we cannot hear you.
that QR
Excuse me, sir.
which is
So your voice is breaking too much. We cannot understand.
independent, the control reversal speed or control reversal dynamic pressure is independent of hello, is there any problem?
So your voice is breaking too much.
Is it okay? Hello?
Sir, we couldn't hear what you said in the
Voice
last
is breaking too
two.
much. Just ah, I'll just connect the headphone. Let me just connect it. Is it okay?
Now it is fine, sir.
Okay, okay. So whatever I was discussing, let me come to that. So with the we have taken two cases. One case is with case 1. We have taken as k delta is infinite, and in that case, whatever reversal speed we got, QR, we got the same value, basically minus QD wing multiplied by CL delta bar by CM delta bar. So apparently what I am saying, basically the control reversal speed is not depend on the stiffness of the control actuator. However, it is depends on the aerodynamic coefficients CL delta bar and CM delta bar, and also the flexibility of the wing. The flexibility of the wing is reflecting in this QD wing, that is wing divergence dynamic pressure, and so just let me come to here. K delta infinite and finite are equal to 0. Reversal speed is same what we have obtained with the K delta is finite, infinite, these two conditions. And then in this case, what we got, if you look at here, eta L is equal to 1 minus Q by QR. If we express in non-dimensional term, then we'll be having 1 minus Q by QR, whole thing divided by 1 minus Q1 bar, then 1 multiplied by 1 minus Q2 bar, B minus BC into Q1 bar Q2 bar. So if you look at here, in this expression, if you go through the denominator part, what it says that this whatever we got earlier with clean FL section without any, we have got the QD wing. With respect to that, including these 2 degrees of freedom, we are getting 2 different values of Q1 bar and Q2. That is meaning is that we are getting 2 different divergence dynamic pressure when we are considering K delta is finite. So that I'll come to the solution of that, how we can get the solution separately. Let us just compare what we got with respect to the K delta is infinite and K delta is finite. In K delta equal to infinite, what we got, alpha are equal to that same thing, Q minus Q D wing CL delta bar by CM delta bar, and K delta infinite, we are getting also same expression. Then we have obtained the eta L for K delta is infinite, 1 minus Q by Q R divided by 1 minus Q1 bar, whereas with the finite stiffness of the control surface, what we got, eta L is 1 minus Q by QR, whole thing divided by 1 minus Q1 bar multiplied by 1 minus Q2 bar minus BC Q1 bar Q2 bar. So apparently what it is coming in the denominator part, we are having 2 different values of Q or the condition for divergence will be getting from here. Basically, if you look at here, the eta L, when it is 0, eta L is 0, that is control reversal speed, and if denominator is 0, that will give us divergence speed. That means denominator is 0, eta L is infinite. So the denominator is 0 will give us the divergence dynamic pressure. Whereas in the finite finite stiffness, we are getting 2 different value of Q. and in for eta k delta is infinite, we are getting one value. That is what we have obtained from our clean aircraft without any control, clean aerofoil section without any control surface. And in this case, what we are getting, this KD wing, Q divergence wing is equal to K theta by E c square CL alpha, and in our with finite control surface stiffness, we have taken another parameter equivalent to this wing divergence, that is QD control surface. This is just to represent that in a non-dimensional form. We have taken it, but physically it is not having any meaning. K delta divided by E capital E c square CMH delta, and then we have the values Q1 bar we are getting Q by QD wing, and Q2 bar is Q by QD control surface. These are the parameters with K equal to K delta is finite and K delta is infinite. Now let us come to the calculation of this. When K delta is finite, the divergence speed will be getting when denominator will be equal to 0. So that is basically giving from we are getting from the expression that 1 minus Q1 bar multiplied by 1 minus Q2 bar minus BC Q1 bar Q2 bar equal to 0. The denominator of the efficiency is equal to 0 gives us basically efficiency of efficiency with finite control surface, that is having two different dynamic pressure under which it will be deflect, means going to divergence. And if we solve this quadratic equation, basically what we are getting here, it is a quadratic equation, and solving this quadratic equation, we can get the two values of the divergence dynamic pressure. And suppose we are getting this condition, that is BC equal to 0, that is B whatever we have considered Cm delta bar plus Cl delta bar, and C we have obtained considered as Cm means alpha divided by Cm means delta. If these two values, product of these two values are 0, then we can say that QD1 is QD wing, QD2 is QD control surface. So this is the special case when BC equal to 0, but usually will not get this BC equal to 0. So BC not equal to 0, and what I have discussed earlier also, B is normally less than 0 will give us this condition. And let's say 1 minus first bracket 1 minus Q1 bar into 1 minus Q2 bar. Then I am taking here the mod of BC multiplied by Q1 bar Q2 bar equal to 0. So this shows that if coupling is there, then QD1 will be greater than equal to QD wing. Similarly, QD2 will be greater than equal to QD control surface. So redefining this concept, that is QD control surface is okay. This already we have defined earlier, and then I am taking this equation 1 minus Q1 multiplied by 1. Sorry, just 1 minute. We have taken it here 1 plus Q2 bar.
Is it 1 minus Q2 bar, sir?
Sorry. Okay. With this condition, actually, we have redefined the control surface. Control surface divergence is minus K delta divided by E c square CMH delta. Instead of plus, we have taken minus here, and then we are redefining Q2 bar is equal to minus Q by Q divergence control surface, and then I am rewriting this expression 1 minus Q1 bar multiplied by 1 plus Q2 bar, minus BC Q1 bar Q2 bar equal to 0. Okay. Then after expanding this equation, I am getting this condition. If you look at here, 1 plus Q2 bar minus Q1 bar minus 1 plus BC Q1 bar Q2 bar, this is equal to 0, and substituting this Q1 bar Q2 bar, we can get here this condition, 1 plus 1 by QD control surface minus 1 by QD wing multiplied by Q minus 1 plus BC divided by QD control surface multiplied by QD wing. So we are getting this quadratic equation. Is it clear now? We have just redefined the Q2 bar. Q2 bar we have taken as minus Q by QD control surface. With that, I have taken it here plus. Then I have once we get the solution of this quadratic equation, we'll be getting as Q D1 and comma 2. That will be equal to minus B plus minus B square minus 4AC divided by 2B. So with respect to that, basically we are getting, this is the value of A. This portion is the value of A in a usual equation, what we write as AX square plus BX plus C equal to 0. So X is, the root of this equation is minus B plus minus square root B square minus 4AC divided by twice A. Just I have taken that way and we have obtained the value QD1 comma 2 is minus QD wing minus QD control surface divided by QD by QD control surface plus minus square root, we are taking B square minus 4AC, so it will be become 4 into 1 plus BC by QD wing into divided 1 plus BC divided by QD wing into QD control surface, and this is with this term minus 2 into 1 plus BC by QD wing by QD control surface. And then we are after simplification we are getting this equation, QD wing multiplied by 1 minus QD control surface divided by QD wing. We are just taking this, multiplying this minus sign, so minus plus, it will be, we are getting this expression. I'll just show you how, because here to find out the value of QD1 and QD2, we need to take some numerical non-dimensional values so that I can finally calculate the value of QD1 and QD2. If you look at here, we have, so if BC less than 0 and BC mod BC less than 1, then we will be getting QD lowest will be less than QD wing. And if K delta is equal to 0, that is floating control surface, hypothetical situation, floating control surface, then we can get QD control surface equal to 0 and QD control surface by QD wing will be equal to 0, substituting this value. So finally we will be getting QD is QD wing divided by 1 plus mod of BC, which is lower than the actual value of the controls divergence of the wing without control surface. This what we are considering is QD wing is divergence of the aerofoil section without considering control surface. And now I'm just showing it. If we take the value of different value of BC and with values of QD control surface and QD wing, we can find out QD by QD wing. So when BC is equal to minus 0.5, this is equal to 0, it will be, I think it is, this is what we get here, 1 plus 0.5. So that will be coming as not in this expression. Actually, we have to substitute in this expression to find out the value, and then we can get a typically plot like this with the increased value of the ratio QD control surface by QD wing. We'll be getting asymptotically, it is coming to the same value, QD wing by QD by QD control surface. This is QD is the divergence speed with control surface. This is divergence speed without control surface, the divergence dynamic pressure. And then we can get this also, you can numerically you can plot it and find see that whether it is you are getting similar expression or not, or means similar plot or not. Okay, with this, I am completing this part, the divergence analysis related to control reversal of the aerofoil section with control surface, means with control actuator, where we have considered two cases with K delta is finite, that stiffness of control actuator is finite and K delta is infinite. Okay. If you have any doubt, just you ask me, otherwise we'll go to the next topic.
So can we have something like a doubt session this weekend?
Okay, see, before going to the 3D wing analysis, if you have any doubt, you can just ask me. Then from the beginning of this chapter, means 2D aeroelasticity, you can ask any question from the 2D aeroelasticity.
And like I think I'll have to revise, and maybe I thought if we can have a doubt session sometime then.
You want to, I think that will be better if we plan for taking a test. So far, whatever I have covered, if you appear for some test, and then you will be revising this portion, and then before test, if you have any doubt, I can clarify that. Is it okay?
Yes, sir.
Okay, sir.
So what we can do, next Wednesday, can we take a test?
So can we keep it next to next week?
Next week. Okay. Then next week. Okay. I think I'll take not more than 1 hour. 1 hour will be little less. Let us plan for some other day. Wednesday itself. Is it okay if I plan for Wednesday?
Coming Wednesday or 2 weeks after this?
2 weeks after this. So
Okay,
that
sir.
you means I'm giving you time to revise it so that we can have a test on that, on the first part, that is 2D aeroelasticity, where I have covered basically linear divergence means solution of a aerofoil section which is mounted on a torsional spring, and then we have taken nonlinear condition I have shown basically the equilibrium equation, how we can get the equilibrium condition, we can get how we can get the stability of the system giving a perturbation, and then from the energy approach I have taken those conditions. Means when we take the first derivative equal to 0, we will get the equilibrium condition, and second derivative equal to 0, that will give us the indication of stability of the system. Then after that I have covered the wind tunnel testing different models, wall mounted model, strut mounted model, and sting mounted model. Then I have just covered this chapter, control reversal. So probably what I can I'll just check the calendar. So if we are planning to have the test on 24th, okay, 24th February, probably 22nd I can keep it for doubt clearing session. Is it okay?
Yes, sir.
Okay, sir.
So 22nd, just before the test, if you have any doubt, we can discuss about those things, and then you can appear for the test. But in the meantime, means 2 days remaining period, and next week I'll be covering the 3D error elasticity related topics. Okay.
Okay, sir.
Okay. So that way we will plan for the test, so that this portion, whatever you have start, means you can get time to go through the entire chapter, and if you have any doubt, we can discuss on it on 22nd. Okay. So I'll continue, or you want to take some break and then we can join for the new session, 3D error elasticity.
So break.
Okay, this is 8:35. So by 8:45 you can join back. We'll start the next part of the class. Okay, 3D error elasticity.
Okay, sir.
Okay. Can I take the attendance now? Rajesh Meena? Rajesh?
Present, sir. Present.
Priyam Dalmia?
Present, sir.
Siddhant Raj Jindal?
Present, sir.
Aman Sangban? Phoni Sai Ganesh?
Present, sir.
Dikshit Rathod?
Present, sir.
Kajal Chaudhary?
Present, sir.
Chandramouli? Yuvraj Kumar?
Sir,
Present,
Chandramouli present, sir.
Yes.
Chandramouli present, sir.
Borun Trishul?
Present, sir.
Aditya Deepak?
Present, sir.
Ajay Tanala?
Present, sir.
Jitendra Pradhan? Kotharpalli Vivek?
Present, sir.
Rahul Raj?
Present, sir.
Kritik Santosh?
Present, sir.
Siddhant Gupta?
Present, sir.
Arghunir Giri?
Present, sir.
Ashutosh Das?
Present, sir.
Kotipalli Lilaram?
Present, sir.
Rafsan Singh?
Yes, sir.
Prajapati Devars?
Present, sir.
Shivam Pandey? Divya Datta?
Present, sir.
Shreyas Samudra?
Yes, sir.
Sai Ashit? Venkata Suryavardhan? Nikhil Pankaj Mantri? Chandu Patil Saitej?
Present, sir.
Devani Das?
Present, sir.
Vishnu Kumar Thakur?
Present, sir. Sir, Sai Harshit present, sir.
Purita? Nitin Sharma?
Present, sir.
Sir, your voice is not clear, sir. No, sir.
No, sir.
हाँ केसरीनाथ चौधरी
Present, sir.
हाँ yeah परिता
Sir. Yes, sir. I'm present, sir.
okay Vignesh
Yes, sir. Vignesh are present.
Tamas Pal,
Yes, sir.
Nadim Rahman,
Present, sir.
Aish Gupta,
Yes, sir.
Prithvi Narne.
Present, sir.
Nikhil Pankaj Mantri, Venkat Satya Shriyavardhan, Shibam Pandey, Jitendra Pradhan, Aman Sangban. Okay. So I'll be starting with this new topic, that is finite wing aeroelasticity. So far, whatever I have discussed, that is with the aerofoil and with a unit span direction, considering that it is from a infinite wing, infinitely rectangular wing, we are taking a small portion and idealizing that in as a two-dimensional model, and then we have studied the effect of aeroelasticity on the on the aerofoil section. Now, in this, we will be taking a finite wing consideration for our derivation of the aeroelasticity analysis. Let me start with this. We can have different type of wing configuration, a straight wing, finite straight wing. We can have this type of rectangular wing where we have to take the effect of support and also the effect of free end. Similarly, we'll have, this is straight rectangular wing and this is straight swept back wing. Means keeping the chord length same, only it is going in the backward direction. That is the what we call as capital rho swept back angle. And then we can have another type, that is tapered wing. Tapered wing maybe in the front part of the aerofoil section or rear part of the aerofoil section, both can be tapered in such a way that we can have this type of configuration. And we can have another what we are calling as the tapered swept back wing. Keeping this rear part of the aerofoil section straight and only front part is slanted or tapered. So that way we can have this type of 4 different configurations. And obviously in this case also initially I will consider the configuration without control surface, clean wing, 3D wing. Then later we will see after introducing the wing portion how we can do the analysis, that part also. So and we can have something like this, tapered wing, where see in this whatever we have taken only one swept back angle, but in some cases we can have two swept back angle, means one is like this, then another in the this means we can have two different configuration of the front part of the aerofoil section. Just let me just draw this, what I am talking of. Basically, we can have this type of configuration, and then from here again different slope, which is basically, if you look at our LCA configuration is similar, this kind of configuration where double sweep back angle is there. And there, obviously, when we will be talking of the finite wing, 3D finite wing, we may not get a appropriate analysis information from the idealized configuration. There we have to do the aerodynamic analysis considering the actual flow pattern of the aerodynamics, and then only we will be able to idealize, or we can see for a actual aeroelasticity analysis for a full aircraft, where the CFD and structural model will be coupled through their interface. And see, when it will be considered like this, let's say this is our aircraft plant model. Due to change in angle of attack, that is theta, will have due to alpha plus theta, and due to this, whatever lift is developed, there will be a change in this theta. So theta 1 will be coming out, and then we have to again, it has to go to the CFD solver, where with the new configuration it will be able to calculate the aerodynamic load, and then it will give back to the aircraft plant model or elastic model. And this way, when it is this control loop system is stable, when it this theta 1 reaches to a converged value. Otherwise, the condition will be considered as a divergence. So, first problem what I am taking here, let's say straight rectangular wing, where we will be considering the this is our aerodynamic axis. See, in the aerofoil we have considered aerodynamic center. The means connecting all the aerodynamic centers for the entire span will be getting as aerodynamic axis. Similarly, we will have a elastic axis, what we have taken earlier also. The movement, whatever will be balancing about this elastic axis, and the length of the wing, finite wing is L, and the forward speed, what we are considering here, U infinity in this. So let us assume that wing is at same rigid angle of attack alpha r, means whole aircraft, means in that case we will be considering that the whole aircraft is with a angle of attack with the full this is the alpha r. We are considering that alpha r is initially given, but due to this alpha r, whatever lift is developed or lift the aerodynamic pressure developed, that will be once it is applied on the structure will not due to flexibility, the structure will not have only the deformation, what means rigid deformation whatever we have given. In addition to alpha r, we will have alpha r plus theta. So that way we will continue the same way the derivation. So in this case, we are the transverse deformation W is a function of x and y. This W will be considering as a function of x and y, the platform coordinate, and W elastic axis, at the elastic axis will be considering the deflection reference, that is the reference axis. And the W is the transverse deflection with respect to y. And due to change in angle of twist, we will be getting the total deflection at any point in the finite wing, the WEA, bending deformation at reference point, minus x into theta y, that is x into the rotational twisting, rotational displacement of the finite wing. And so that way we have to take basically here we are taking two different degrees of freedom. One is the bending deflection, another is a torsional deflection. So considering these two degrees of freedom, we have to take two equilibrium equations. One is the bending equilibrium equation, and another we have to take twisting equilibrium equation. Is it clear why I am saying why you have to take these two configuration, means two equilibrium equations? Because see, with the finite wing, when load is acting through the aerodynamic center, that will be creating a moment about the elastic axis. If you look at here, whatever elastic axis we have taken, it will be rotating about this. In addition to the bending deflection, it will be also rotating about the elastic axis. So that way we have to subtract this WEA minus x into theta y.
Sir,
Why
is that
we
like
have
the deformation due to bending and the deformation due to twisting? Is that
yeah.
like it tries to reduce the deformation of bending due to bending? Is that
No,
the
no,
case?
no.
Yes,
It is like this. See, if you look at here, we are taking the deformation. The bending deformation is the downward is positive. Okay, this is positive, and in our definition, this pitch up moment, pitch up deformation is theta. So, if you look at that, suppose this is our elastic axis towards the front part, that will be having x coordinate. Okay. I think I'll come from this information. Actually, coordinate will be here. Our coordinate origin of the coordinate will start from here, x coordinate, and with respect to this, we'll have this side will have a negative value, and deflection, when we are substituting the value of x here, the deflection is actually positive. So upward deflection, actually upward deflection is the bending, not this one. Sorry, actually deflection, and lift also will be taking in that direction. So L EI into del 4W by del y to the power 4 plus lift, distributed lift, that will be taking as the equal to 0 bending equation. Is it clear how I am taking? See, in this is the origin of the coordinate. If you look at here with respect to from here, we are going backward. This is the x positive, and this is y positive, y coordinate positive. So if I am going to the front part, that will be, if I take in this with respect to the coordinate system, this side deflection will be, so that is WEA
sir, is the
minus,
x is along
yes,
wing tip to wing root or along the chord?
no, from the elastic axis, from the
Okay.
elastic axis to the rear part of the wing. Sorry,
Along the
aerofoil section.
fuselage of the fuselage.
Yeah, along the fuselage, towards the back side of the fuselage. This is the origin.
Sir, but
X,
for
X is in, yeah.
sir, but for we have to take different value of x for different cross sections, right? Because
In this case,
along the cross section theta will change.
okay. The assumption here is that whatever rotation will be there, that torsional rotation, that will be about elastic axis. That means along the chord length, it will be constant. What you are
Okay, sir,
saying,
and from sir, and from what point should I measure x? Like, will it be the aerodynamic center?
No. It is from the elastic axis, elastic center. This is the elastic axis. This is aerodynamic center. Aerodynamic pressure will be developed about the aerodynamic center. Resultant pressure will be acting through the aerodynamic center. However, the equilibrium equation we have to consider about the elastic axis. So the coordinate is starting from the elastic axis towards the rear part of the fuselage, and in that sense, when deflection, so bending deflection, bending at elastic axis, bending deflection minus this will be coming this way. See, this will be, let's say, at this point x. So due to this theta, whatever deformation will be there, we are ignoring that tan theta will be equal to theta. That means small theta. So it will be coming as x multiplied by tan theta. Okay, this will be the length. Means
Yes.
okay.
Sir, and
That I am
about the
approximating
elastic, on the elastic axis, there will be zero deformation, right?
No, at elastic axis we are not taking zero deformation. We are taking this value WEA at the elastic axis, and in addition to that, due to rotation, torsional rotation, it will be having additional bending deflection. That bending deflection is coming due to this.
Yes.
From here, whatever at any distance, it will be with the minus sign, minus x into theta into y. That means towards the trailing edge, we will have the bending deflection less, whereas towards the front side of the aerofoil section, it will be higher, because there x will be with the negative sign, negative value. Okay. So
Sir, bending elastic axis is same as neutral axis, right?
yeah, neutral axis. Yeah. Basically, elastic axis is coming from your shear center concept. You have gone through the shear center
Yes.
concept. No?
Yes, sir.
So
Yes, sir.
at each cross section, whatever shear center is acting through that cross section, if I connect all the shear centers, it will become the elastic axis. Okay. So if
Yes,
I consider the equilibrium equation, see here the lift force is acting through this aerodynamic center. So it will have the bending equation will have the EI into del 4 W by del y to the power 4 plus distributed lift over the span direction, half span direction, and this lift force, which is eccentric, that will be giving torsional moment. So MA is coming from the lift. One part will be coming from the lift. Lift will be inducing a aerodynamic moment, and also due to the camber of the aerofoil. So that way, finally, we'll be having two equations. First equation is the bending equation. If you look at here, this bending equation is coupled with theta, but it is not coupled with the this equation. Means this theta, this equation is independent of W. If you look at here, this theta is independent of W, whereas the bending equation is coupled with theta. If you look at here, if I substitute this information from the in the bending equation, then I will have both bending deflection plus torsional rotation is coming into picture. Whereas in the second equation,
what is L and MA?
L is the lift, distributed lift per unit length. See, in this case, let me just go back 1 second. This wing, we are this rectangular wing, we are idealizing as a cantilever beam, and its bending stiffness and torsional stiffness is acting through this elastic axis. So with respect to that, I am taking just think that it is a 2 dimensional beam model, idealized beam model, where aerodynamic load is acting through the aerodynamic center, and equilibrium of the this finite wing will be considered about the elastic axis. And if I take the equilibrium equation of the bending equilibrium equation, I will be getting this EI multiplied by del 4 Wy by del y to the power 4 plus distributed lift. This is lift distribution, means whatever we have taken unit length we have multiplied earlier will not multiply by 1, will be taking as lift, will be taking as Q Q into C into CL alpha into alpha r plus theta. Okay, and if you look at here, this first equation is having both component of W and theta, whereas in the second equation we will be getting only the rotational moment, which will be Gj d2 theta by dy square, and Ma is coming from here, one part is coming from here, lift into eccentricity plus the whatever aerodynamic inherent aerodynamic moment is there about the aerodynamic center. We will be substituting in this equation, and then we can get the complete value of moment about the elastic axis. So if you look at that way, first equation is the coupled equation, whereas second equation is uncoupled equation. Second equation, we don't need W to be substituted in the second equation to find out the rotational deflection. That's where actually what we can say that in a aeroelasticity analysis, usually bending is not influencing the deformation. We have considered, if you look at in the beginning, I have discussed about why we have taken the modal concept. We have taken only the torsional mode. We have not considered for the aeroelasticity calculation the bending and torsion both together. We have taken to find out the aeroelastic equilibrium condition or aeroelastic divergence condition, both coming from our torsional concept, torsional equation, because torsional deformation will give rise to the additional lift, whereas due to bending there will not be any additional lift. But due to rotation, this twisting of the wing, it will be inducing some additional aerodynamic bending moment on the first equation. Okay, so that's where I'll be taking with respect to the second equation. We'll be solving it when we are taking a straight rectangular wing. We will not solve these two equations simultaneously. We will consider only second equation. We will not consider the first equation. Is it clear? Where will be I will show the equation where these two will be coupled. These two will be coupled. Whatever I am giving the argument here to ignore the first equation, that will not be valid for certain conditions. That is basically in the swept back wing, where bending and torsion will be coupled. In a straight wing, as bending is not inducing any additional torsion or torsional deformation, so we can decouple the second equation from the bending equation, whereas the bending equation is dependent on the torsional equation. As we are interested only with the aeroelasticity effect, that's why I am taking only the second equation. I am not taking in the straight rectangular wing concept or in the swept back, tapered wing. We don't need the first equation to be considered. Whereas when we will be considering the swept back wing, tapered swept back wing, then we have to consider both the equations. We have to take this equation and also this equation in the consideration.
Sir,
Yes.
so can you explain like how the induced lift is getting generated?
Induced lift.
Like you said in the second equation, due to theta rotation, twisting of the airfoil, some induced lift is getting created. So like how is that happening? Can you explain that?
Okay. I am coming to that equation. I'll just show you here. See, here, when I am writing Ly, lift will be Q into C into Cl alpha into alpha, and alpha function of y I am taking as alpha r plus theta function of y. And if you look at the bending moment, so it will be coming Q E C square Cl alpha multiplied by alpha y, and we will have Q C square Cm naught. So in this equation, if you look at here, this moment, aerodynamic moment is having only alpha r prime and theta. We are not getting any W component in the lift force, whereas in the lift force distribution, in the moment there is no W component, whereas in the lift calculation we have theta component, torsional component. That's where I am saying, if you look at, okay, if you look at here, this equation will have, after substituting, will have W and also theta. So this W and theta, they are coupled in the first equation, whereas in the second equation, whatever aerodynamic moment is, that aerodynamic moment is independent of W. There is no component of W coming into picture in this second equation. That's why I am saying this equation is coupled, whereas this is uncoupled. Means coupled in the sense the W is dependent on theta, whereas theta is not dependent on W. Theta is independent, whereas in this case W is dependent on theta. Am I clear now?
Yes, sir. So you mean to say we have to solve fourth equation and then substitute that theta in third equation?
Yeah. First,
Sir, but
means
what is
this
the
separately
induced
I can
lift?
solve.
But what is the induced lift?
Induced lift, that is coming due to this deflection, no? Due to torsional deflection, the induced lift will be coming because this is the rigid angle of attack, and due to deflection, the additional lift is coming here. That is the induced lift due to flexibility of the finite wing. Is it clear? This whole part is the lift force. This is the lift force.
So QC Cl alpha into theta is induced lift.
Theta is basically induced because due to flexibility, this theta, see, when we are considering that the aircraft wing is infinitely rigid, then theta will not be appearing. For rigid, it will be 0. So there is lift. Means if you are giving alpha, let's say 5 degree, it will whole aircraft will be experiencing 5 degree. Whereas if we are considering that this aircraft wing is flexible, then this theta will not be constant. It will be variable over the entire length. In our first assumption, means idealization, where we have idealized the aircraft wing as a beam model.
Sir, then QCCL alpha into theta will be the expression for induced lift, right?
Yeah. That will be the
Oh.
induced lift. QCCL alpha to theta y. That is the additional term due to flexibility, what it is coming into picture. That is basically we can consider as the induced lift. Induced lift due to flexibility of the wing structure. So just let me show you. Suppose we are considering here the beam as a torsional member. The beam is subjected to a system of distributed twisting moment. Then let us consider that we are taking here a small distance dx, and this distribution of the bending moment is uniform. We are considering here. So suppose we take the equilibrium of what are the forces acting here and what are the forces acting here. So all the moments, if I take, this is minus t, I am taking clockwise as positive, minus t plus m into dx, the aerodynamic moment, plus t into dt equal to 0. So we are getting finally, after simplification, this dt by dx, that is derivative of torsional moment divided by dx, means derivative with respect to x should be equal to the distributed moment over the length. That is the meaning of this equation. And then substituting the value, we are getting again d theta by dx can be calculated t by gj d theta by dx. If you look at in the torsional derivation, we have used this means we have derived it. D theta by dx is equal to t by gj, that is slope per unit length is equal to t by gj. Then after substituting this, we will be getting this equation d by dx multiplied by gj into d theta by dx. We are just taking from here, from this equation, t equal to gj multiplied by d theta by dx, and taking this, substituting in the first equation, whatever equilibrium equation we have obtained, if I substitute there, then d by dx into gj d theta by dx equal to minus m. This this m is basically distributed moment, aerodynamic moment over. And suppose we are taking a rectangular, then gj can be considered as constant. Then we can write it as d2 by d2 theta by dx square gj, taking gj outside. I am taking this as minus m. But if this is not constant, suppose we have a tapered, then obviously I cannot take gj is constant. G may be constant. If material is same, then g may be constant, j may not be constant. So in that case, I have to see the distribution of j, how it is varying over the length, and then accordingly I have to substitute here. I'll be showing that derivation once we come to tapered wing configuration and how to calculate the this governing differential equations and how to get the solution. First I am taking it is a straight rectangular wing, then I can write this expression as Gj d2 theta by dx square is equal to minus m, and that's what I have shown it here. So Gj into d2 theta by dx square plus m equal to 0, that is torsional equilibrium equation, and bending equilibrium equation is nothing but d2 by dx square ei d2 w by dx square equal to 0. Again, when ei is constant for a straight rectangular wing, I can take out ei outside, so I can write it as ei d2 4 w by dx to the power 4 is equal to p, or minus p equal to 0. So this is the two equilibrium equations when we are considering a finite wing, idealizing as a beam model, idealizing that as a beam model. This is the beam model we are considering, means we are considering the beam which is having 2 degrees of freedom. One is w and theta. See, don't misinterpret this theta is like a bending slope. It is not bending slope. In our derivation, we are considering this theta is torsional rotation of the beam, and w is the bending deflection. Bending deflection will be taking upward positive, upward whatever we have taken it here in our positive axis system, it will be positive upward. Sorry, just 1 minute. Yeah, positive upward with respect to our right hand screw rule. So it will be positive coming from here. So upward positive. Finally, when I am idealizing this finite wing as a beam model, we can get the equations, two equations like this. One is the torsional equilibrium equation, what we are getting Gj into d theta by dx square plus m equal to 0, considering that it is a straight rectangular wing, and similarly considering the straight rectangular wing, beam bending equation can be idealized as d2 by dx square whole thing multiplied by ei into d2w by dx square, and finally we can reduce it to this equation. That is the equation I have considered here. If you look at here, we have first we have calculated the lift distribution. Lift distribution will be q into c into cl alpha into alpha y. This alpha y will be having two component, alpha y, alpha function of y, means one is constant part alpha r plus theta function of y, and the bending moment, aerodynamic moment can be calculated. One is coming from the lift distribution. This is the moment due to eccentric lift force, because lift force is not acting through the elastic axis, it is acting through the aerodynamic center or aerodynamic axis. That's why due to that eccentricity we will be getting the moment q e c square into cl alpha multiplied by alpha r prime plus theta, when I am taking this into consideration inside. So it will be alpha r prime plus theta. So now if we write the equilibrium equations, we have first bending equations ei del 4 w by del y to the power 4 plus q into c into cl alpha. We have alpha r plus theta function of y equal to 0, and then another equation will be getting torsional equation, that Gj multiplied by d2 theta by dy square, that plus q e c square cl alpha whole thing multiplied by alpha r prime plus theta function of y equal to 0. So if you look at here, if I want to solve these two equations simultaneously together, then we need to get means substitute this means after simplifying this first equation, whatever I have written it here, this equation, I will be getting this fourth order equation EI del 4 W by del x to the power 4 plus Q C CL alpha theta function of y equal to minus Q C CL alpha into alpha r, that is the bending equation, and torsional equation I will be getting as G J d2 theta by d y y square, sorry d. Okay, I think somewhere I have used x and some places it is y. In this case, we are taking as y as the coordinate, gj d2 theta by dy square plus q e square cl alpha into theta function of y, that is equal to minus q e square cl alpha into alpha r prime. So, if I want to solve these two equations, if you look at here, I need to integrate this equation 4 times. So, I need to apply 4 boundary conditions here. I need to apply 2 boundary conditions here. So, what are those boundary conditions for beam bending equation? What are the boundary conditions? Suppose we are considering a cantilever beam, then the boundary conditions are like this: at y equal to 0, I will have w and dw by dx equal to 0, and at the free end, what we will be substituting the force boundary condition, that bending moment shear force equal to 0.
Shear force will be 0.
No, bending moment also will be 0 at the free end. At the free end, bending moment, shear force both will be 0. So that's where we will be getting d2w by dx square equal to 0 and d2 cube d cube by d cube w by dx x cube equal to 0. This is equal to bending moment and this is equal to shear force, equivalent to shear force. So that is the 4 boundary conditions what I am talking it here. Is it clear?
Yes, sir.
Suppose we are taking the simply supported beam, then both the ends deflection will be 0 and bending moment will be 0. Those boundary conditions will change. And in the torsional equation, suppose I am taking this torsional equation, means boundary condition for this cantilever beam. So at y equal to 0, theta will be equal to 0. At y equal to L, what T will be equal to 0. Torsional moment will be equal to 0. That is nothing but d theta by dy equal to 0. So these are the two boundary conditions for second equation. The four boundary conditions whatever we will be getting from the getting for a cantilever beam for the first equilibrium equation. So suppose we are defining here, the defining y bar equal to y by L, we will define like non-dimensional parameter here. The span length we are expressing in terms of y bar, that means normalizing with respect to the length of the wing, y by L. We have taken the cantilever wing, so the total length I am taking it here as a capital L, this length capital L. So y by L is the non-dimensional length coordinate. So if I take the derivative with respect to this x, so dy bar equal to 1 by L dy, and substituting this relation in this second equation, if you look at, I will have gj by L square d2 theta by dy y bar whole square plus q e c square cl alpha and theta function of y bar, and right hand side will be q e c square cl alpha into alpha r prime. Now dividing whole equation by L square by Gj, sorry, dividing whole equation by Gj by L square. So this term will become Q E C square L square CL alpha by Gj theta y bar, and right hand side will be Q E C square CL alpha L square Gj alpha r prime alpha r prime. And now we will define this term as a lambda square. This term will be taking as lambda square. So if you look at here, whatever we have taken the second equation, if I take lambda square here, this will become lambda square and this will also become lambda square. So if I write it here, the d2 theta by dy bar whole square plus plus lambda square into theta y bar minus lambda square by alpha r prime. So we can get the solution of this equation, where we will have the solution from homogeneous equation and particular integral for this equation. So if I get the solution of this equation, it will be the homogeneous solution will give us a sin lambda y bar plus b cos lambda y bar minus alpha r prime. This will be coming, this is the, let me just write it, homogeneous solution, and this is particular integral. Is it clear this solution, how I am getting it? Basically we have to consider d2 theta by dy bar whole square plus lambda square into theta function of y bar. This is equal to 0. This is the homogeneous solution of the equation. That means if I am taking theta function of y bar as let us say a1 e to the power lambda into y bar. So taking second derivative d2 theta by dy bar whole square, I will be getting a1 lambda square into e to the power lambda y bar. So after substituting this equation, I will be getting as in this expression. So I will have a1 lambda square. Oh, sorry, I should not take lambda here because I have taken lambda here. I should take beta here, beta square. So beta square e to the power lambda y bar plus lambda square theta into y bar. Sorry, theta I will be taking as a1 e to the power beta into y bar. This is equal to 0. So simplifying from this equation, we will be getting as beta square plus lambda square equal to 0. So this will give us basically beta is plus minus I lambda. So plus minus I lambda, once I substitute, I will be getting a sin lambda y bar plus b cos lambda y bar, and let me just see whether I have another. And particular integral, when we will be calculating, that is d square plus lambda square multiplied by theta y bar. This is equal to lambda minus lambda square alpha r prime. So if I take the particular integral y bar, I will be taking as 1 by d square minus lambda square, and taking this lambda square into alpha r. So once we simplify this expression, we will be getting as alpha r prime. So finally, whatever equation I am getting here, let us see the solution. What we are getting as theta y bar equal to a sin lambda y bar plus b cos lambda y bar minus alpha r prime. That is the solution of this equation. And now we have to substitute boundary condition, two boundary condition to find out the integration constant. A and b are the two integration constants. So if you look at here, so the boundary condition what we are going to substitute, putting boundary condition at y bar equal to 0, I will be taking theta is equal to 0, at y bar equal to 1 at the tip of the cantilever wing, that should be t equal to 0, t or my distribution of moment equal to 0, that will be giving us basically gj theta prime equal to 0, that is nothing but theta prime equal to 0. So if I take this equal to theta prime, if I am taking from here, means first derivative of theta, so it will be I'll be getting as a lambda cos lambda y bar minus b lambda cos sin lambda y bar. Then substituting these two boundary conditions at y bar equal to 0, theta is equal to 0, and at y bar equal to 1, theta prime equal to 0, that will give us the solution like this. From applying the first boundary condition, we will be getting as in this equation b equal to alpha prime, and from the second equation we are getting a equal to b tan lambda. So alpha r prime tan lambda. So finally theta y bar will be getting as substituting in the first the solution equation where we have got this solution. So after substituting, we will be getting alpha r prime multiplied by tan lambda sin lambda y bar plus cos lambda y bar minus 1. So this is our final solution.
Sir, but
of the
what will be the value of the particular integral?
Value of the particular integral is coming as a alpha prime only.
So like we can,
I'll just show
like,
you
can we
here.
express it in terms of some lambda square or something?
Let me just show it once again. This is d square plus lambda square into theta y. Okay, this will be equal to minus lambda square alpha r prime. So if I take this way, theta y, this will be the particular integral. This will be minus lambda square alpha r prime, and if I take lambda square outside, so it will become 1 plus d square by lambda square. Okay. So taking in the binomial expansion, taking first term, because if I take, this is a constant, if I take derivative with respect to this, it will become 0. So it will become minus alpha r prime into 1 plus d square by lambda square inverse, and expanding it, taking the first term, I will have alpha r prime plus minus d square by lambda square plus 2 factorial d square by lambda square whole square, and we will have infinite terms. I am saying as it is a constant, if I take higher order terms, anyway differentiation will become 0. Okay, that's why I'll be getting from here only the first term minus alpha prime. That's what I have taken it here. Is it clear?
Yes, sir.
So actually, whenever we have to do the particular integral we have to do this way. If you look at back your engineering mathematics, means when a homogeneous means some governing differential equation equal to 0, then we get one solution. If right hand side equal to non-zero, then we have to consider two parts. One is the homogeneous solution, another is the particular integral. Homogeneous solution, what I will be getting it here, whatever I have shown earlier. So basically exponential form we will get, and lambda will be getting as beta will be getting as plus minus I lambda, which will be expressed in the exponential form or trigonometric form. Both are similar, either exponential form or the trigonometric form. And the particular integral, after doing this manipulation, will be getting as alpha r prime. And then what I am saying here, basically I will be taking the two boundary conditions, boundary conditions I have to substitute here. When I am taking y bar equal to 0, y bar equal to 0, I am substituting in this expression. So this will become 0, this will become 1 minus alpha r prime, right hand side equal to 0. So alpha r prime is b, we can express, b is the integration constant. I am able to express in terms of alpha r prime. Okay. And then from the second equation, what I am saying, first derivative equal to 0. So a lambda cos lambda minus b lambda sin lambda, this is equal to 0, this is equal to 0, and this lambda, lambda y bar, it will be, y bar I am substituting as 1, and then finally I am getting the integration constant a in terms of b. So a is b tan lambda, which I can which I am expressing in terms of r prime tan lambda. So finally theta as a function function of y bar is coming as alpha r prime tan lambda sin lambda y bar plus cos lambda y bar minus 1. This is the final solution for a 3D finite wing where we have idealized the straight rectangular wing as a cantilever beam, and we have taken 2 degrees of freedom w and theta, as w is only coupled with the theta, whereas theta is not coupled with w. I am taking the second equation and getting a solution.
So theta, alpha r is the initial, angle of attack.
Initial angle of attack. Alpha r is the initial angle of attack. Whatever we are rigid angle of attack we are giving to the full means, though I am idealizing here this way, fuselage is there. The clamped part is basically fuselage. If you look at here, the support is with the fuselage. This is actually with the fuselage. Sorry.
Yes.
This is with the fuselage. With the fuselage, wing is connected. And fuselage is considered as a rigid structure, and that's why I am taking that boundary condition as the clamped boundary condition. And this is a cantilever wing portion that I am idealizing as a beam model initially, but because see in the this error elasticity theory, whatever we will be discussing, basically we are idealizing in such a way that we will be able to get the solution. First I have taken as a the aerofoil section is mounted on the torsional spring, and I got the solution. Now here I am taking this this become a cantilever wing idealized as a cantilever beam model, where fuselage is considered as the rigid and wing is fixed at that point. So that is the fixed boundary condition I am applying here, and at the free end I am applying the free boundary condition. So that way I am taking the equilibrium equations and getting the solutions also. So first equation I have not considered, just to get the solution here. I am taking the second equation and then getting the solution, this solution, and then I am substituting the boundary condition. I am finally getting the solution in this form. Theta y bar is alpha r prime tan lambda sin lambda y bar plus cos lambda y bar minus 1. So, here basically what we are getting, a definite value of theta, deformation theta will have a distribution. If you look at here, theta I can calculate from 0 to 1. Theta y, if I substitute 0, what will happen? This will become, this part will become 0, y bar, this will become 0, and this
Theta y will be 0.
theta, yeah, theta y bar equal to 0. And then we can, substituting the values of y bar, let us say 0.01, 0.02, like that I can get a distribution of this theta distribution over the span. Here if you look at whatever I have taken the configuration, you will be getting something like this, the theta distribution, or I will be getting theta distribution something like this. So, at support it will be 0 due to clamped boundary condition, and it will be sinusoidally increasing up to the tip of the cantilever wing. Okay.
Yes, sir.
Okay, I think you may have some class, so we will stop here. And if you have any doubt, you can ask now, or next day we can have again, just discuss once again about this and then continue. If you don't have any question, then you can leave now. Okay, thank you.
Thank you.
Okay.
Okay.